right, so this is the first VCast where we're going to actually look at how stars, specifically our sun and stars like ours, will eventually evolve and change throughout their life cycle. And before we get into notes, it's very important that you have your HR diagram from the previous section of this unit. It should look similar to this. Because we're going to be drawing on it, adding to it, and it's going to be very useful as a diagram to show how stars like our sun change and evolve over time. All right, so one of the more important facts to start off with, stars in some ways are actually very simple. They all are made out of hydrogen and helium. And the same basic forces govern their majority of their lifetime. They all burn hydrogen, in their cores at the beginning, but everything about how long they're going to live, their size, temperature, color, luminosity, how long it lives, how it will die, all of these properties that can be described about a star really boil down to how much mass did it start off with. Because again, they're all pretty much hydrogen and helium, and they all go through nuclear fusion. The question is, well, how long will they do that? How hot are they burning? And it really just boils down to the mass. How much mass did they start off with? So we will describe several different evolutionary paths, and they're all based on a range of masses. We're going to start, in this case, with just low mass stars. And particularly, we're going to look at our sun. What is going to happen through the course of our sun's lifetime? Now, first off, our sun, just to kind of review what's going on, is currently in hydrostatic equilibrium. That means gravity is balanced out with that internal pressure. That internal pressure is the radiative pressure and the electromagnetic repulsion. Okay, those forces balance out gravity, and that's why it's not shrinking or growing. Hydrogen and helium are fusing inside the core always. Again, that's what causes that radiative pressure. That helium is slightly less massive, so mass is being turned into photons, pushing out. And what happens is then it's going to do this for like 9 to 10 billion years. All right. Just like a car that starts off with a full gas tank, in this case, the sun's core gas tank is full of hydrogen. It starts using up that fuel, that hydrogen, and instead of expelling the helium out the tailpipe of this car, it just kind of builds up. So our core slowly begins to fill up with helium, the waste product. Think of a fire. You put wood in, you start burning it. For the most part, it turns into ash, and the ash stays in the fire pit. It starts to fill up. That's what's going on in our star currently. Now, why is this helium? Is it going to fuse? Is it not going to fuse? What's going on there? Well, remember that it took 10 million degrees to slam the hydrogen together to make helium. Helium is not fusing yet inside the sun because it's just not hot enough. You need much, much higher temperatures to fuse helium together. And if our sun continues to heat up, and if it ever does get to 100 million degrees Kelvin, it could take that helium and fuse it into other heavier elements. But it's not doing that yet. It's roughly about 15 million degrees in the core currently. So we're a long ways off. So what's going to happen when our sun actually runs out of fuel? Because again, that helium is taking up more and more space. We're running lower and lower on fuel. And just like any car, if you don't fill up that gas tank, the fuel will run out. And when that fuel runs out, that means there's going to be no more radiative pressure, because hydrogen can no longer fuse into helium if there's no more hydrogen. And think of our analogy with these forces. We've had two small kids on one side of a teeter-totter bouncing off a much heavier kid. All right, that's been our analogy here. One of those two small kids, the radiative pressure, have jumped off the teeter-totter here. So our forces are now unbalanced, just like that teeter-totter, and what will happen is hydrostatic equilibrium is thrown off, the core is going to shrink. All right? When things compress, the temperatures are going to rise. All right, pressure is going to increase, and we will reach a point at where we will hit 100 million degrees Kelvin. That helium that has been sitting around building up inside the core will begin to ignite in something called the triple alpha process. We're going to have heliums, 3 of them, coming together to make a carbon atom. All right, so we're going to have a new reaction start inside the core. All right, and that carbon will start to grow just like the helium had been growing. Since we have a new reaction here, hydrostatic equilibrium gets balanced, so the core stops shrinking. At 100 million degrees, burning helium, all right, in this layer, all right, into carbon. So let's take a look at what's going on at this point. So after 10 billion years of hydrogen fusing into helium, the inside begins to separate into different layers, like an onion. And each layer has a different reaction. The yellow here, hydrogen is fusing into the helium, which sinks down. That helium starts burning into carbon. We get this carbon core growing here. That's what's going on in this much smaller, hotter core. But if you were in a spaceship looking at this star going through this change, you would not see a star that shrinks. You would actually see that since the radiative pressure inside is much stronger, you would start to see that our star starts to expand. That expansion causes it to cool off on the outside, and it becomes a yellow dwarf, or excuse me, a red giant. In fact, our sun in 9 to 10 billion years, when the core begins to shrink like that, it's going to, on the outside, grow into something, potentially a star the size of the orbit of Mars. A much, much bigger object called a red giant. So the core and the outward appearance are doing completely opposite things, which is interesting. So grab your HR diagram here. All right. You should have a little object in here called the sun, that you plotted right about here. And what we're going to do is we are going to make the first line, all right, indicating that our sun, after spending pretty much 90% of its life cycle here on the main sequence, is going to turn into a giant. So go ahead and indicate that transition from the sun on the main sequence down here up into the giants. This is our first transition. So our sun is going to turn into a red giant. And again, I said the orbit will be the size of Mars. So if we're still around in after 9 billion years of hydrogen fusing into helium, at this point, the Earth will be gobbled up by the sun. The solar system will look totally different at that time. But this stage, this red giant stage, only lasts 1 billion years. And this is because it's using way more fuel. It's doing it much faster. So this reaction of the carbon core growing and taking up that core is going to happen very, very fast. Core will eventually collapse, just like the last time, once it runs out of fuel to use, increasing the temperature. And if you could get the core to 600 million degrees Kelvin, that carbon could burn into oxygen by combining with another helium, and so on across the periodic table. But our sun will not reach that temperature because it lacks the sufficient amount of mass to crush the core to these extreme temperatures. At that temperature, or at those, you need the electromagnetic repulsion is way too strong to for the gravity to overcome. So carbon will not combine into higher, heavier elements on the periodic table for our sun in particular. That really is going to be, for the most part, the end of our star being a true star, where nuclear fusion is happening inside of it. What we're going to see at this point is that the solar winds, because the core has gotten much smaller and hotter, is increasing the solar winds, and layers are actually going to start to blow off of our sun, forming what is known as a planetary nebula. Planetary nebula do not have planets in it. They don't form planets. But there's some of the coolest things to look at. These are red giants throwing off their outer layers, and those outer layers making these very cool, intricate patterns, which are then illuminated by the hot remaining star. Once those layers, though, drift away, all you are going to be left with is that very small, very hot, very dense core that is what we call a white dwarf. All right. White dwarfs are approximately the mass of the sun. Okay, they don't have to be exactly the same mass of the sun, but they are approximately the mass of the sun, crushed down to the size of Earth, containing all carbon. There is no more fusion happening here. And it's not a true star because there's no more fusion. They do give off light because they are hot and they glow, but there's no fusion. So let's go back to our HR diagram once more. And I want to... You're going to come over here, all right, to the white dwarfs. This process here is where it is a planetary nebula, but it turns into a white dwarf. And as white dwarfs cool off, they will eventually fade and drop off of the HR diagram to where it is called a black dwarf. Other than that, a few things I want to do just to wrap up here. This is the path for our sun. It is also the path for anything that has a similar mass range. So there's no more fusion. Again, damn it, I already went over this. Let's just get rid of that and discuss it here. This path that I'm going to use the black pencil for is good for low mass stars. And they have a range of upward of 8 solar masses, so things that are roughly 8 times more massive than our sun, all the way down to about 1/4 of our mass. There are slight variations and differences in the end result, but they will go through these giant stages: planetary nebula, white dwarf, black dwarf stages. And that's basically everything that we need to know about how our sun and other low mass stars will evolve and change.